Hey everyone, welcome to the video for Module 6.3.3. This is the last video in this unit, and this will be discussing tension among other factors. So as a whole, a muscle fiber is either contracted or relaxed, which we consider the all or none principle. And the tension produced by the contraction of an individual muscle fiber can vary, and that depends on the number of pivoting cross bridges, the fiber's resting length at the time of stimulation, and the frequency of stimulation. But tension production is greatest when a muscle is stimulated at its optimum length. There is no mechanism to regulate the amount of tension that's produced in a contraction by changing the number of contracting sarcomeres. And when calcium ions release, they're released from all triads in the muscle fiber, and thus the muscle fiber is either contracting or relaxed. So, in the length tension relationship, which we hinted at earlier in this module or in the unit, the number of pivoting cross bridges depends on the amount of overlap between thick and thin fibers. And there's an optimum amount of overlap to produce the greatest amount of tension, but too much or too little overlap reduces the efficiency. Normal resting sarcomere length is about 80 to 100% of resting length of maximum overlap. In the frequency of stimulation, a twitch is a single stimulus contraction, relaxation sequence in a muscle fiber that can vary in duration depending on the muscle type, location, and the internal and external environmental conditions. A single neural stimulation produces a single contraction or a twitch, which lasts about 7 to 100 milliseconds. And sustained muscle contractions require many repeated stimuli. The length of a twitch depends on the type of muscle. And then a graph of muscle tension, when it's developed, is called a myogram. And twitches are divided into three phases. You have the latent period before contraction, in which the action potential moves through the sarcolemma, causing the calcium ions to be released. Excitation contraction coupling is occurring. The action potential is sweeping across the sarcolemma down the T tubules and stimulating the release of the calcium ions. At this point, the muscle is not producing any tension. You have the contraction phase, in which calcium ions bind to troponin, the tension builds to its peak, and when the cross bridge formation is occurring and tension rises to a peak. As the tension rises, sarcomeres are shortening to their maximum. Lastly, you have the relaxation phase, in which calcium levels fall, the active sites are covered, and tension falls to resting lengths. And when calcium is no longer available, binding sites are being covered and no more cross bridges occur. This lasts about 25 milliseconds. The length of the twitch depends on the type of muscle. And again, a graph that shows this is called a myogram. Repeated stimulations immediately after the relaxation phase causes a series of contractions with increasing tension. This stair-step type increase in twitch tension is called TRPE. The gradual increase in the force of contraction within a muscle caused by repetitive stimulations of the same strength after complete relaxation has occurred, and sometimes called the staircase effect. Repeated stimulations before the end of the relaxation phase causes increasing muscle tension called summation of twitches or wave summation. Stimuli arrive as relaxation begins as the muscle never fully relaxes between contractions. This causes larger contractions. If rapid stimulation continues and the muscle is not allowed to relax, the muscle twitch will reach a maximum level of tension called incomplete tetanus. Basically, incomplete tetanus, a muscle producing almost peak tension during rapid cycles of contraction and relaxation, and the muscle tension eventually hits a plateau. If stimulation frequency is so high that the muscle never begins a relaxation phase, the muscle reaches what we consider complete tetanus or continuous contraction, and occurs when the stimulation are so rapid that there's no time for the muscle to relax. The amount of tension a whole muscle can produce depends on the internal tension produced by the muscle fibers, the external tension of the muscle fibers that exert their elastic extracellular fibers or series of elastic elements such as tendons, and the total number of fibers stimulated. We hinted on muscle unit or motor units earlier, but just to recall, a single motor neuron controls hundreds of muscle fibers, considered a muscle unit, that contract at the same time. Motor units, or all of the fibers that are controlled by a single motor neuron. The number of muscle fibers in a motor unit can vary greatly, and the fewer the number of fibers in a motor unit, the more precise the contraction is. The muscle fibers of each motor unit intermingle with those of the other motor units, and the smooth but steady increase in muscle tension produced by an increasing number of active motor units is called recruitment. A variable number of motor units is always active, even when the entire muscle is not contracting, and this creates that resting tension called muscle tone that we talked about previously. During sustained contraction, motor units are activated on a rotating basis called asynchronous motor unit summation, and this ensures that each muscle unit has the opportunity to recover before it's stimulated again. Two factors help to determine the amount of tension that's produced by a skeletal muscle. One, the amount of tension produced by each stimulated muscle fiber, and two, the number of muscle fibers stimulated at a given moment. In a whole group or group of muscles, remember that the smooth motion and increasing tension are produced by slowly increasing sizes or number of motor units stimulated. And remember, this is called recruitment or multiple motor unit summation. A single motor neuron can control hundreds of muscle fibers that contract at the same time. And this goes back into our classification of muscle contractions, in which isotonic contraction, the tension rises until it exceeds the load so that the load is moved. Once the load moves, the tension in the slow muscle now remains constant. And remember, those two types are concentric and eccentric. Concentric, where contractions permit the muscle to shorten, and eccentric, in which contractions that cause the muscle to lengthen. And you also have isomeric contractions, in which the tension increases to the peak, but the muscle neither shortens nor lengthens. Instead, the tendons tend to stretch. When maximum tension is achieved, when all the motor units reach tetanus, but this can only be sustained for a short time. Sustained tension is less than the maximum tension, and this allows some motor units to rest in rotation. When considering the development and regeneration of muscle tone, during embryonic development, groups of embryonic cells called myoblasts fuse together to form a multinucleated cell called a skeletal muscle cell. Skeletal muscle cells are enormous. Each muscle cell may possess hundreds of nuclei. And some myoblasts do not fuse. Instead, they remain in the endomysium, forming myosatellite cells, which are important for the repair of damaged muscle cell. If a muscle cell is damaged greater than the extent that can be repaired by the satellite cell, the muscle fibers are replaced by scar tissue in a process called fibrosis. Similar to skeletal muscle tissue, cardiac muscle does not regenerate to a great extent. Dead cardiac muscle tissue is replaced by scar tissue, which cannot contract. Smooth muscle tissue can regenerate from a type of stem cell called a pericyte, which can be found in some small blood vessels. Pericytes allow for smooth muscle cells to regenerate and repair much more readily than skeletal muscle and cardiac tissue.